morning, guys. Can you hear my voice?
Yes, sir.
Yes, sir.
Okay, let me share my screen and we will start today's class. Is my screen visible?
Yes, sir.
Okay, today we'll discuss memory management. But before that, in the previous class, we discussed deadlocks. Let me go through that just 2 minutes, then we will get back to the memory management. So, deadlock is like whenever the number of resources uh, are hold by other process and waiting, keep on waiting, then there is a deadlock. Suppose T1 is holding R2 and requesting for R1, but this resource is held by another process and it is keep waiting. There is a cycle. We can say that there is deadlock. Even though you don't understand anything, you remember only this method, deadlock avoidance. Deadlock avoidance is one of the method that is used in operating system. Before, in order to avoid the deadlock, we have to make sure that system is in safe state or not. The safe sequence, in that sequence, if you allot, then you will not enter into deadlock. So you have to find the safe sequence. The system should be safe or not. So we understood by one example like we have maximum needs and current needs for this threads, and we have these resources. If you allocate in this order, instead of T0 first, if you allocate T1 first, the available resources, then T0, T2, the order in which you are allocating resources makes your system into a safe state. It will not go into deadlock. If you alter this order, there are chances that you may go into deadlock. So you have to make sure that safe sequence is carried out to make sure that system is in safe. In which order, based on the availability of the resources is met or not, we have to make sure the system is in safe or not. So one method is resource allocation graph. Like if there is a cycle, if allocating resources makes a cycle, then there are good chances the system will go into deadlock. So avoid that. Though make sure that when you are allocating resources, there are no cycles. This is one method. The other method is Banker's algorithm. In Banker's algorithm, we have to take care of only three things, three steps. Like the three steps are, I mean, like first you have to make sure the system isn't safe or not. This is the safety algorithm, and this is the request algorithm. Once you are sure that system isn't safe, then you have to allocate the resources based on the need. So these are the typical number of instances, allocation graph, maximum available graph, and the resources available. These are the available number of instances. A has three instances. A resource is having three types of instances. B resource is having three types of instances. C is having two types of instances. This is the allocated matrix, and this is the maximum needed, maximum requested. So the need is max minus allocated. Will give you the need. Based on this need, based on this available, which thread could be satisfied, you allocate that resource only. See, thread 1, thread 0, A needs 7 instances of resources, but we have only 3. If you allocate this available resources to thread 0, then system will go into deadlock. But if you allocate T1 first, T1 is meeting the need. So you can allocate T1 first. Then your system will not go into deadlock. This will be satisfied. Thread 1 will finish its execution. After thread 1 finishes its execution, then the number of resources available, the available matrix will be the resources which is used will be added to available because it's finished its job. Okay, after finishing its job, the resources holding by thread 1 will be released, it will be available. Then we will keep checking which other resources can be uh, up, we can provide the resources so that the system will not enter into deadlock. So these are the simple things you keep in mind. This is how the banker's algorithm works. Banker's algorithm is very important algorithm to avoid deadlock. Okay, so these are the things we need to keep in mind. But rest of the things, how deadlock prevention, deadlock uh, uh, like you want to recover from the deadlock, those are all things you can go through it. But these are the predominant ideas where the deadlock avoidance can be used using banker's algorithm in our current situation. And having discussed this, let us today discuss about memory management. So we will discuss today the memory management. Uh, One of the main responsibility of the operating system is how we are managing the memory. In memory management, there are two parts we need to consider. One is main memory. The second is virtual memory. Uh, this week we will discuss main memory, the issues in main memory, how the main memory will work. All these things we'll discuss. Today class we will not be able to finish. We need Thursday class also. So we will start discussing this main memory with respect to memory management. We'll see how much we can finish today, and rest of the things we will try to cover on Thursday's class. And after that, we will discuss the virtual memory. So memory is a central to the operation of modern computer systems that we know. Memory consists of large arrays of bytes, and each memory location has its own address. That also we studied as a part of data structures. Also we studied in arrays. Also we understood that memory consists of is nothing but a storage space in terms of large array of bytes with its own address. The CPU fetches instructions from memory according to the value of the program counter. Typical instruction cycle, when I say that when an instruction is executing, the typical cycle follows like this. The instruction is placed in the memory, means when you are writing a program, it will be converted into executable code, which will be placed in the memory by converting that program into a process, right? So it will be placed in the memory. First, the CPU fetches the instruction from memory. Instruction is then decoded and cause the operands to be fetched from the memory. And after instruction is executed on the operands, results again stored back in the memory. Okay, results after that particular program is executed, the output, the result is again placed in the stored back in the memory. Typically, the memory where the processor takes the instruction, and after finishing its instruction, the result will be placed in the memory bank. So main memory and the registers built on each processing core, uh, but the registers are placed in the motherboard, which are close to the processors. These instructions are taken from the main memory. To mismatch the speed, there is cache memory is placed in between. But for the time being, we will assume that now processor is taking from the main memory. The same mechanism you can apply for the cache memory also. Okay, but for the time being, we'll try to understand the main memory is the idea. uh, we'll carry on further. The machine instructions that take main memory addresses arguments, but none then take the disk addresses. So any instructions in execution or any data used in the instructions, therefore should be stored in the direct access storage device. If data is not in memory, they must move before the processor can operate on them. Because unless the instructions are in the memory, you cannot you cannot execute it. If you want to execute an instruction by CPU, you need to move that into memory first. If the data is not in memory, CPU cannot operate on that. So they must be moved first to the memory, then from memory the processor will take instructions. So when you are converting an each program into a process, so typically in the main memory looks like this. Some space will be occupied by the operating system. Some space, some memory bytes will be occupied by the operating system. Then after that, for each process, whatever the memory is required, we will allocate, the main memory will give some space to each process. Now, there is a difference, base and limit. Suppose for this process, each process must be separated. Each process should be allocated in separate memory space. Each process has a separate memory space. You cannot overlap. You cannot overlap the processes. So each process will keep separate memory space. So to allocate each process a separate memory space, we need to ensure that the address of that each process will be unique. Okay, so this process, suppose there is a memory space available here, and for example, let us take this process. So this process, the base address is 30040, which means that the process, suppose it takes, the program takes this many addresses, the limit of 12,000 addresses, 12,000, sorry, how much is this? 1 lakh 20,900. Okay, this many addresses for a particular process is needed. So the base address, we will start from here, and we will allocate this many memory locations towards uh, this is the address available. This is the to total space available. It will calculate the available space. So the base address plus the amount of address is needed, we will add them, and it will take for 4,20,940. So the address from 3 lakh 40 to 4 lakh 20,940, the address space of all these values belongs to this particular process. Okay, this memory will be allotted to this process only. Okay, the maximum amount of space we will calculate, and whatever the address space is available, those many address spaces we will allocate. So likewise, for each process, there is a base address, and the amount of process that is required, we call that as a limit. Base plus limit will give you those many address spaces. We will allocate them to a particular process. So the base register holds the smallest legal physical memory address. The limit register specifies the size of the range. Is this clear?
Yes, sir.
Yes, sir.
So the problem here is how the CPU will calculate the address, how the main memory will store the address. They both are different. Okay, the address that is generated by CPU, we call them as a logical address. The address what is stored actually in the main memory, we call them as a physical address. So when a CPU is generating an address, we will verify that for the particular process, when an address is generated by the CPU, we will compare with base and base limit. The address that is generated by a particular process, should be greater than base and less than base plus limit. This both conditions should satisfy. Okay, when an address is generated by the CPU, that address for a particular process, if it has to store, if it has to access, if it has to do some manipulations, Thus, address in that for a particular process should be greater than or equal to base and less than or equal to base plus limit. Means, suppose there are so many memory locations here. Uh, if a particular the memory CPU is trying to access and do some manipulations for this process, that address should belong to greater than or equal to base and less than or equal to base plus limit. It will verify. We have to verify this. Base should be greater than or equal to then only yes, and it should be less than or equal to base plus limit. If either of this condition fails, if it is no, then there is some illegal addressing error. Operating system is trying to take the illegal addressing error. We will generate an problem of addressing this error. Then if this both condition satisfies, if the CPU generated address is greater than or equal to base and less than or equal to base plus limit, then we will try to access, and then only will be allowed to access the main memory. So this scheme prevents the user program accidentally or deliberately modifying the code or a data structure of either the operating system or for the other users. In terms, it will not disturb the other processes. Okay. So the base and the limit registers can be loaded only by the operating system. This base address and the limit address will be loaded only by the operating system. Is this clear?
Yes, sir.
Okay, let us now try to understand the address binding. Whenever you are generating a source program, you are converting a program, the compiler will convert your source program into your object file, right? You would have studied in first year C programming uh, how a user program is converted into a executable code. When you compile your program, your source program, what your C program or Java program or Python program, when you compile it, it will compile and create an object file. And when an object files are created, these object files are linked with other object files which are required via linker. Okay, this is the compile time, this is the load time, where the linker will connect the object file based on the source program and other necessary object files. It will link, convert that into executable file, exe file. In once it is turned into executable file, it will load. The loader will come into the picture to load this executable file into the memory by dynamically linked libraries. Using loader, it will load into the memory. Here we will run the program. This is called execution time. How much time it will take for execution based on your program. Typically these are the steps when you convert your program, and when you're seeing the output, execution time or run time. Typically the steps behind the screen, what happens is you are converting your source program into object file, and this object file is loaded into the memory and it will run. Okay, so these are the typical steps. Now, whenever a source program is generated, there are some addresses that are associated with. We need to allocate some address or some memory for that particular program. We need to bind the address for that particular program. So addresses in the source program are generally symbolic, such as variable count. You can declare variables. You can suppose you declare int a is equal to 5, int a. You are reading some variables. You are storing some value in a variable. That variable should be allocated some space. Suppose you are saying int a is equal to 2. Suppose integer will take 2 bytes. The 2 bytes of memory should be allocated in the main memory for that particular program. So those how it is binding, we will understand. So typically the addresses in the source program are symbolic. A compiler typically binds these symbolic addresses to a relocatable addresses. Suppose 14 bytes from the beginning of this module. Then linker and loader in turn binds that relocatable address to the absolute addresses. Each binding is a mapping from one address space to the other. We will try to see. So the address binding, we need to understand what happens with respect to compile time, load time and execution time. In compile time, uh, the process will reside in memory. Absolute code can be generated. In load time, if it is not known at the compile time where the process will reside in the memory, then the compiler must generate a relocatable code. In execution time, if the process can be moved during its execution from one memory segment to another, then binding must be delayed until runtime. Usually on the behind the screen, this happens, but what we have to understand is when a program is generated, we need to understand the difference between logical address and physical address. Okay, the logical versus physical address space. Here say there is a space. What is relocatable? Real Whenever you are generating a program, when you compile it, it should reside. The process should reside in the memory. It will generate an absolute code, that is an object file, or the absolute code that will be understandable by the processor. When this is not happening, the absolute code is not generated by the compiler, then the compiler must generate a relocatable code. Again, it has to generate some code. Then in the execution time, that code, the process should be moved from memory segment to one memory segment to another memory, and binding will be delayed until the runtime happens. So how the program is generating some space, how we are reallocating, how the memory is moved from one segment to another segment, how the binding will be delayed until runtime. These are all few things we need to understand. But to understand this, let us now get into a deep understanding of how the memory management will happen. So memory management unit, this is the main thing that we need to understand, how the memory management unit will have will work in an operating system. Typically, in memory management unit works in two addresses, that is logical versus physical address. Whatever the address that is generated by CPU, we call that as a logical address. That memory management will help us to handle uh, to make to understand whatever the address that is generated by CPU, logical address, will be understandable by the memory management unit, and it will convert this logical address into physical address, and it will store in the physical memory. So an address generated by the CPU commonly referred as logical address, whereas address seen by the memory unit, that is one loaded into the memory address register of the memory, is commonly referred as physical address. Okay. So usually this happens in operating system. The runtime mapping from virtual to physical address, means logical address to physical address, is done by a hardware device. We call that as a memory management unit. This is a hardware device which will convert into logical address into physical address by memory management unit. Now, what happens in address binding is the binding addresses at either compile time or load time generates identical logical and physical addresses. The execution time address binding scheme results in differing these logical addresses, usually refer to logical addresses is also called as virtual addresses. All this set of logical addresses generated by the program, we allot them as a logical address space. The set of all this physical address corresponding to the logical address is a physical address space. So we will generate logical addresses, and the set of all the logical addresses generated by a program is a logical address space. The set of all physical addresses corresponding to the logical addresses is a physical address space. So what happens in execution time is address binding scheme. This logical and physical address spaces differ. They both are different. Okay, they both are different. So the user program, whenever a user is writing a program, he deals with the logical addresses. The memory mapping hardware converts this logical address into physical addresses. We have two types of addresses. So logical addresses can be in the range of 0 to maximum. Suppose a process wants some memory of uh, some amount of memory. Logical addresses usually we will range from 0 to max. But physical addresses on the main memory, we will not uh, keep them as a range. we will keep them the range that is available, range plus 0 to range plus maximum for the base value of R. The user program generates only logical address. Think that the process runs in the memory from locations from 0 to max. But however, logical addresses must be mapped to physical addresses before they are used. Suppose you are generating a program, suppose you are writing a program, you are saving, say, program.c. You are generating program.c. This program needs to execute, you including all the variable counts, array, you declare structure. For all these declarations, some memory will be allocated by the program. So we will not worry about from which location to which location in the main memory this program will reside. As a user, I will calculate this program.c. Let us say that it takes 100 bytes. Maximum, it takes from 0 to 100 bytes. So the logical address says that this program will require 0 to 100 bytes, maximum in the range of 0 to 100 bytes. That all I'll worry. How much a program will take uh, for a particular program in order to execute, how much of memory it is required, that all I am worried. That is logical address. But this 100 bytes, where it will paste in the physical memory. For example, we observe that here the physical memory, if this space is available, it can be placed here. If this process is finished, it can be placed here. In which location it is placed, on which particular addresses, because this address is also physically available in the RAM, that address we will consider them as a physical address that is given from the range. That range we will take, that base address range plus 0 and range to max for the base value of R. That's what we discussed, base plus limit. So this is the physical address, and actually in the main memory that is stored. But as a user, when we are writing a program, we will worry only about logical addresses, think that the process runs in the memory from 0 to max. However, on the background, the operating system converts that logical addresses into physical address. They will map from logical address into physical address. Does this make sense?
Yes, sir.
Okay. Now we need to allocate. Suppose that's where the reallocation will come into the picture. Suppose we studied here. So whenever you are compiling a program, that process should reside in the memory, generate an absolute code that could be generated. During compile time, this will happen. During load time, if the compiler is not able to generate the code which should be reside in the memory, then it will generate a relocatable code. If it is relocatable code, then it should be moved from one memory segment to another memory segment, and binding should happen during the runtime, which will be delayed slightly because of relocation. So let us now try to understand the relocation. Dynamic relocation using relocation register. Suppose the CPU generates the logical address 346. This is the logical address of 346. Now the base register, whatever we generated, we call that as a relocation register, because once you are executing a code, that execution by the processor will generate the logical address. Now relocation register or a base register, we have the availability, the newly available space is, say, relocation register is 14,000. Now the logical address takes 346. Now the memory management unit will calculate the relocation register is 14,000 and the logical address is 346. So the memory that will be physical address is simply the relocation register plus logical address. It will keep in the memory at 14,346 memory location. Okay. It will simply add and see that if that space is available. The physical address is simply relocation register plus logical address. It will kept at 14,346 at the memory location. So simply that will happen. Okay, I think it's copied 2 times. Is this clear?
Sir,
It
the
takes care of memory management unit. Memory management unit will takes care of relocation register. This address after generated by the CPU, that memory management unit will calculate based on the logical address, based on the relocation register, it will generate a physical address. Yes, what is your question? Somebody's.
yes, sir, this physical address is the limit to which the memory can be stored, right, sir?
No, this is the base address. Relocation register is a base address.
Yes, sir, the physical
For
address is physical address is the limit to which the memory can be stored, right, sir?
physical address is the amount of
14,000.
memory it is stored. Yes. See,
Yeah.
when a program dot C it is generated, if it is generating 346 means this program dot C will take 0 to 346 address space. Okay.
Yes, sir.
Now we need a physical address. How it will calculate? We need to have a range. The range available R should be there. Now the range, the physical address will vary from R plus 0 to R plus max. That's what we studied in the previous slide. 0 to max, R plus 0 to R plus max. Now the logical address is generated by CPU. CPU generated 346 and the range that is available relocated register, that is a base value of R. That is a base register. P, that is a base register. Base register is the relocation register. The base register R is 14,000. Now the physical address is mapped from 14,000 to 14,346.
Yes, sir. So shouldn't the address now, like, shouldn't it now point to 14,000 and not 14,346? Because
No, yeah.
14,003.
So based on this relocation register, from 14,000 to 14,336 up to this, that process will occupy. Now
Okay,
the
sir.
relocation register will be updated by 14,347. For the next program, it will be available 14,347, something like that.
Yes, sir. Okay. Thank you.
Suppose if you give 14,000, then the next program will allocate from 14,000 onwards. Then it will overlap.
Yes, sir. Understood.
So the next available space for the relocation register should be, so it says that till 14,346, it's occupied, something like that. Okay.
Yes, sir. Yes, sir.
Okay. Now the main issue is how the memory allocation is happening. Like for example, you have this memory. Suppose some part of memory is taken by operating system. Say some process P1 is there, some process P2 is there. P2 is finished. Suppose let us say that this memory space is available. This process is allocated by this program.c from 14,000 to 14. Okay, PGM. Okay, program.c. So if a new program is coming, if a new process say P2 is coming, will it allot here? If this space is free, this space is free, this space is free. Will it allot here or here? So how the operating system will decide at which memory location particular process should be loaded? It will verify. It has to verify. Suppose there are many parameters here, right? Suppose this program, suppose here the available space is only 20 bytes. This gap is available only 20 bytes. Then program say it required say 30 bytes, then it cannot allot here, right? The space is not sufficient. It has to allot here. Suppose it is 10 bytes, it can allot here. So there are various issues. How a operating system will decide at which memory location a program should be given some memory space is also is also a difficult issue. Is also an important issue. So usually the memory is divided into two partitions, one for the operating system and one for the user programs. So as I told, even if you see this in the first slide, some part of this memory will be occupied by operating system. Then these are the user process. User is executing some process. Always some part of memory will be occupied by the operating system. Now, when an operating system starts, the memory allocated for the operating system will be on the top of the memory or on the bottom of the memory. You can allot anywhere, but many of today's logical, we can place the operating system either low memory address or high memory address. This decision depends on the many factors such as location input vector, but many operating systems, including Linux, Windows, place their operating system in the high memory. We will assume that you can keep anywhere because they depends on many factors, but many operating systems keeps the operating system on the high memory value, that is on the top. You see this is the example that we can see that the address starts from 0 from bottom. The maximum address it will go to, this is what, 10 lakhs, say 1 million. But the operating system is kept on the top addresses. Okay, this is the memory space that is taking by operating system, that is the high memory. So many of the operating systems that are kept nowadays in Linux or Windows, they kept on the high memory, but 0 to that memory which is not occupied by the operating system, this memory will be allocated to user process. User process, when they are generating from 0 to the remaining memory will be allocated by the for the user process. Okay. So that's the typical way how the operating systems nowadays handled by Linux and Windows. In continuous memory location, each process is contained a single section of memory that is continuous to the section containing to the next process. So whenever we are allocating some process, this entire process P1 will take its continuous memory. Some part of, suppose it is take 30 bytes, 20 bytes I'll allot here, 10 bytes I'll allot here, then it will become non-continuous. Non-contiguous. So memory space will not allocate in non-continuous. It should be continuous memory allocation. The memory space that it's available for, if P2 takes 30 bytes, if it is not available that 30 bytes here, it will allocate here only. Okay, it will not allot 20 bytes here and 10 bytes here. It will not allot. The memory for the particular process should be continuous. Okay, so in continuous memory location, each process contained a single section of memory that is continuous to the section containing the next process. So in continuous memory location, we need to understand first the memory protection, because that whenever you are allocating some memory to a particular process, that should not tamper by the other process. Okay, so the relocation register or the base register contains the value of the smallest physical address. The limit register contains the range of logical address. Okay, so the logical address must fall within the range specified by the limit register. Okay, so relocation and the limit, this is the base address we studied, the range, the whatever the address that is generated by a particular process, it should fall within this range. The memory management unit maps this logical address dynamically by adding the value in the relocation register. Then this mapped address is sent to the memory. Okay, so the allocated memory for a particular process will be generated by relocation register and the limit register. So we should be very much careful in that. So this is we studied again, like the limit register is there, a CPU generate the logical address. If it is less than the limit, then the relocation register is added to the physical address of the memory. If the logical address is less than the limit register, then there should be an error. It should generate the error, and the hardware support for the relocation in the limit registers. This is the same thing that we discussed earlier. The continuous, when we are making a continuous memory location, we need to consider the limit register and relocation register, and we will add that will be mapped into the physical address. Is this clear?
Yes, sir.
Okay, let us now consider one more aspect. Now, one of the how you will allocate the memory for the particular process in a variable sized partitions in memory, uh, where each partition may contain exactly one process. So there is a problem. For example, we'll discuss these examples. Suppose there are some blocks available in physical memory. Let us assume that there are blocks available. Suppose this is 10k, this is 10k block, this is 20k block, and 30k block, and 40k block. Now let us say that you have three process P1, P2, P3, P4. Now P1 needs, say, 5 kilobytes of memory. P2 required 10 kilobytes of memory. P3 required, say, 15, and P4 requires, say, 20. These are the information available with us. Now, which process you allocate to which memory space? P1 can go to, say, this is block 1, this is block 2, block 3, and block 4. Okay, so we have variable sized partitions in the memory. This is the variable size partitions. We have different partitions in the memory. Each partition may contain only one process. If you are allocating block 1 one process, the other process should not go into that particular space. Now P1 is coming, it needs 5 kilobytes. It can go to block 1, it can go to block 2, it can go to block 3, it can go to block 4. It can go and take the block at any value, any block it can take and finish its job. Now in which order you will allocate the particular process to the particular block? Okay, in this variable partition scheme, the operating system keeps a table indicating which parts of memory are available, which parts of memory is occupied. Suppose P1 takes, say, block 4. P1 is allocated in block 4. Now this entire block will be occupied by P1. Although it requires only 5 kilobytes, it is taking, assume that before block 4 is allocated to P1, then no other process will come into that particular block. Okay, so now operating system will say that block 4 is occupied by P1. So when P2 is coming, for P2 it is 10 kilobytes. Now it will say that block 1, block 2, block 3 is only available. So P2 can decide in either one of this block based on the available block. It cannot go in, it can go in any block. It will be fit. Suppose it say that it will go into B3. P2 will go into B3. Now P3, P4 is there. P3 cannot go in B1 because it needs 15 kilobytes, but the available space is 10 kilobytes only. It cannot go in B1, right? So it should go in B2 only. P3 will go in B2 only. You allocate in B3, and P4 cannot allocate it in B1. It has to wait. Okay. Initially, when the memory is available for the user process, one large block is available. We'll call that as a hole. Eventually, you will see that memory contains the set of holes of various sizes. Once this blocks is divided, we will see that of various sizes. In which order a particular process will allocate to particular block is again an interesting problem. That's where the continuous memory location will come into a picture. Like, so suppose let us say that initially operating system is having process 5, process 8 and process 2. Process 8 finished this job, it will create a hole. This space is available. Now process 9 is coming, so it needs only few amounts of memory. This memory is allocated here and this memory is still available, and after that process 5 finished, so this memory space is available. So initially all the memory of the user process is considered as one large block of available, we call that as hole. But eventually the memory contains set of holes. You see this is one hole, a set of holes, this is another hole, because process 5 finished and it will create a hole. Initially all the memories are free, that is one hole, but it will create after the process will come and occupy finished job, it will create some set of holes. This will make us the variable partition. Is this clear?
Yes, sir.
Now with these available holes, suppose if this is the state, that's where the variable size will come into the picture. Suppose this space can be 10k, this space can be 20k, this some other process can be 30k and 40k. Now when the new process is coming, and which block you will allocate which process will create an issue. That's where we call that as a dynamic storage allocation problem, which now concerns how to satisfy a request of n from the list of free holes of n programs. Okay, so we have three strategies. One is best fit, one is first fit, best fit and worst fit strategies, which are the commonly used to select the free hole from the set of available holes. First fit says that allocate the first hole that is big enough. Whenever you are searching the memory space, if a particular process is available, whenever you are searching from particular space, whenever there is a free space available, first you found out there is a hole that is big enough, you allocate it. Search can start either at the beginning of the set of the holes or the location where the previous first search ended. We can stop searching as soon as we find the free hole that is large enough to allocate, to make sure that a particular process will fit into that block. This is first fit. Best fit says that allocate the smallest hole that is big enough. So in this case, instead of allocating P1 to 40k, the smallest available space for P1 could be B1. If you allocate P1 to B1, that is the smallest space that can able to fit. In order to save the memory location, best fit says that allocate the smallest hole that is big enough. We must search the entire list. We have to make sure the entire list unless it is ordered by size. So this strategy produces the smallest leftover hole. In worst fit, it will allocate the largest hole that is available. We must search again the entire list unless it is sorted by size. This strategy produces largest leftover hole. Largest leftover hole is, suppose P1 takes 5 kilobytes, we allocate it in block 4. How much memory is wasted here, unused here? In block 4 takes 40 kilobytes, P1 takes only 5 kilobytes. How much memory space is wasted here?
So 35.
35, right? Because this block is like having capacity 40 kilobytes, but P1 is taking only 5 kilobytes. 35 kilobytes went into waste. That is leftover hole. We call this as a fragmentation. This is called external fragmentation that we will discuss later. Okay, so there the largest leftover will be kept. But in best fit, here we are allocating 10 kilobytes. When P1 we kept here, then the leftover will be only 5 kilobytes, right? If you allocate P1 in block 1, still there will be leftovers, but instead of 35 kilobytes, 5 kilobytes is the smallest leftover. Okay, that happens when you give the best fit approach. First fit, whenever there is a big hole, that will allocate. We will discuss some examples. Let us say that the first method. Suppose job 1, that is process 1, needs 90 kilobytes, job 2 needs 20 kilobytes, job 3 needs 50 kilobytes, and job 4 we have 10 kilobytes. We have 5 blocks available. Block 1 of 50 kilobytes, block 2 100 kilobytes, block 3 90 kilobytes, and block 4 200 kilobytes, and block 5 50 kilobytes. Now job 1 in order to allocate for a particular block, it will verify. First, it will verify in block 1, 90 kilobytes is greater, it will not allocate. Then job 1 will search the block 2. 100, yes, it is available. This space is available, it is large enough. The first fit method says that allocate the first hole that is big enough. So 90 is sufficient to enter into block 2. So 90 will be allocated in block 2. Job 1 will go into block 2. If 90K is allocated in block 2, the unused space in block 2 is 10K, right?
Yes,
Job
sir.
1 needs 90K. We allocated block 200K, which is sufficient. The unused space is 10K. Now job 2 will come. Job 2 will need only 20K. It will keep searching block 1. Block 1 is large enough. So block 1 is allocated to job 2. So job 2 will be taken by block 1. The unused space here is 30K because 50 minus 20, 30K will be unused in block 1. Job 3 will come. You cannot allocate in block 1. You cannot allocate in block 2. Job 3 will come. It will search. 90K is available. This is sufficient enough. So job 3 will go into block 3. Job 3 will go into block 3. Here unused space is 50 minus 90, 40K. Job 4 of 10K will come and it will take block 4 because this is sufficiently large enough. It will come and take block 4. The unused space is block 4 is 190. Block 5 is not used. It is actually this is null. We haven't used the block 5. Okay, unused means we haven't allocated any process. This should be null. Is this clear how the first method allocates the memory?
Yes, sir.
Now let us understand the best fit method. Best fit method, in order to allocate job 1, what it will do is it will search the entire blocks. If you cannot allocate 90K in 50K because this is not sufficient, it will keep searching block 2, but here unused space is 10K. It will keep searching the other list. 90K, 90K, 90K is sufficient. The unused space is less. So the best fit says that the smallest hole that is big enough. So the smallest hole it is creating here is 90K, 90K. So job 1, the best fit for job 1 is block 3. So job 1 will be allocated as per the best fit block 3, and the unused space is 0 bytes, 0 kilobytes. Job 2 will be allocated here. If you allocate 20K, it will be 30 units. Here if you allocate here, then it will be 80 units. Here if you allocate, this will be 180. Here if you allocate again 30. So it doesn't make any difference. So you can allocate here. So job 2 will be allocated the best fit in block 1 because this is the smallest space, unused space that is taking. So job 2 will take block 1. Then here the unused space is 30K. Then 50 unit will come. You cannot allocate in block 1 because you have only 30 units left and it is already taken by job 2. You cannot, you can, if you allocate job 3 in block 2, then unused space will be 50 units. If you allocate here, that will be 150 units. If you allocate here, then it will be 0 units. So job 3 will take block 5. That is the best fit. Job 3 will go into block 5. So here the unused space again will be 0 bytes. Then job 4 with 200K, you cannot allocate in anywhere but here. So here also unused space is 0. Job 4 will take block 4. Here block 2 is not used at all. It is not used, so the memory is nil. So here the unused memory is just 30 kilobytes. When a new process is coming, you can allocate to block 2. Is this clear how the best fit works?
Yes, sir.
Now the worst fit works with the same example. Uh, I think, yeah. Okay, let us now see the worst fit example. Now the worst fit example, let us say that we have 10K, job 1, job 2 20K, job 3 30K, and job 4 70K. Worst fit says that for this particular block, whenever there is a large block is available, you allocate that. Okay. So for job 1, for the 10K, which is the largest block, block 4 is the largest space. So job 1 will allocate to block 4. Job 1 will take block 4 because this is the largest space available, right? Allocate the largest hole. Worst fit says that allocate the largest hole. Now, in worst fit, it will take uh, 1 will go to block 4 because that is the largest space. So block 4 will be occupied by job 1. Job 2 is 20K. Next largest space is block 2. 20K will go to block 2. If job 1 10K will go to block 4, the unused space is 190 kilobytes. Job 2, the next biggest is block 2, 20K. Then unused space is 80K. The next is 30. 30 next largest is block 3. If you allocate 30 units here, then the unused space is 60K. Next job 4, you cannot allocate it because you cannot allocate in block 1, you cannot allocate in block 5. So only 3 jobs will be able to allocate in the continuous memory location. Then the unused memory is very huge. Okay. So this is how the best fit, worst fit, and first fit method allocates the dynamic storage in the memory based on the holes available for that particular process. Is this clear?
Yes, sir.
Yes, sir.
Okay. So whenever you are allocating some memory, there is some leftovers is coming, some unused memory space is coming, right? Where you cannot allocate the particular process. You see the same amount of memory is available, same amount of blocks are available, but in best of it will be able to allocate 4 memory blocks all the efficiently, but in worst fit will be not able to allocate any process. And here you see that block 1 takes only 10K and it is allocated in block for 200K. This 190K memory space, we call that as a external fragmentation. Okay, this is called external fragmentation problem. We'll discuss that in next class. In Thursday's class, we'll discuss what is this external fragmentation. This unused space, although see we have 190K, this process job 70K can be allocated. We cannot do that. This memory space is available, but still will be not able to allocate that. This is called external fragmentation. We'll discuss this fragmentation in the next class. Fragmentation can be internal and external, but this memory space when you are allocating, although you have space, but still you will be not able to allocate for the new process because it is occupied by the other process. We call that as a external fragmentation. We'll discuss that what is external fragmentation, internal fragmentation, how to handle that in the Thursday's class. We'll stop here. If you have any doubts up to this point, please ask. This is not required. I explained this details in the slide itself. Best fit, worst fit, first fit. This is also not required. Okay, so I'll upload this slide. You go through them. From fragmentation onwards, we'll discuss in the next class.
Okay, thank you, sir.